All right, let's kick things off with a question that's so simple, but when you think about it, also pretty profound. It's something you've probably wondered about yourself, just lying in the grass, staring up at, well, one of the most common things we see every single day. I mean, really, you look up and there it is, this huge, beautiful canvas over our heads, and its color is just so certain. But why that color specifically? And that's a fantastic question, because in physics, things don't usually happen by accident. The reason the sky isn't, say, a brilliant shade of purple actually shows us one of the most amazing interactions between the light from our sun and the very air that we're breathing. So let's dive in and unpack this whole thing. To get to the bottom of our blue sky, we first have to look at the source of all that light, the sun. The first piece of our puzzle starts with the light it sends hurtling our way. That's right. It's kind of wild. What our eyes just see as plain white or maybe yellowish light is actually a team effort. It's the full spectrum of colors you can imagine. We're talking red, orange, yellow, green, blue, and violet, all traveling together in one single beam of light. Now, here's the thing. Not all these colors travel the same way. They move in waves, and each color has its own unique wavelength. Just look at the difference here. Blue and violet light travel in these really short, choppy waves. Meanwhile, red and orange light use these long, kind of lazy, stretched out waves. This difference in their wavelengths, it's absolutely crucial. It is the key to this whole mystery. Okay, so we've got our sunlight with all its different colors. Let's talk about the second ingredient we need for a blue sky, our atmosphere. It might look like there's nothing there, but it is far from empty space. It's actually more like a bustling highway of teeny tiny particles. Our air is mostly made up of nitrogen and oxygen molecules, and these guys are unbelievably small. We're talking way, way smaller than even the shortest wavelength of visible light. So I want you to just picture that sunlight with all its colors, making its journey to Earth and having to navigate through this dense sea of tiny molecules. And this is where it all comes together. This is the magic moment. We've got our sunlight with its different wavelengths, and we've got our atmosphere full of tiny molecules. When these two meet, they don't just, pass each other by. No, they interact in a very specific and honestly, a really beautiful way. There's a name for this process. It's called Rayleigh scattering, named after the physicist who figured it all out. And the definition here really says it all. It's what happens when light bumps into particles that are way smaller than its own wavelength. Exactly like what happens when sunlight hits the molecules in our air. And here it is, the golden rule of Rayleigh scattering. Because of their short, choppy nature, blue and violet light are way more likely to get knocked off their path when they hit an air molecule. They get bounced around, they get scattered. But what about the long, lazy waves of red and orange light? Well, for the most part, they just power right on through. So let's just trace that journey for a second. As sunlight shoots into our atmosphere, that blue light immediately starts colliding with gas molecules, and it gets scattered in every direction you can imagine. Up, down, sideways, you name it. This happens again and again all across the entire sky. So eventually, our eyes, looking up from the ground, see all this scattered blue light coming at us from all over the place, which makes that entire dome above us look blue.
Okay, wait a minute. This is a great question for anyone who's been paying close attention. The physics says that violet light, with its even shorter wavelength, should actually scatter more than blue. So, why aren't we all living under a deep violet sky?
Well, there are a couple of things going on here. First, our eyes, they're just not that sensitive to violet. We are biologically built to see blue way more vividly. And second, a good chunk of that violet light actually gets absorbed way up high in the atmosphere before it even has a chance to get down to us. So when it comes to what we actually see, blue light just plain wins the day. The best proof that this scattering theory is true isn't something you see at noon. It happens at the beginning and the end of every day. Sunsets, they aren't an exception to the rule. They are the ultimate confirmation of it. Think about it. When the sun is low on the horizon, its light has to take a much, much longer path through the atmosphere to get to your eyes. It's got to slice through way more air and way more molecules than it does when the sun is directly overhead. So at midday, right, the light takes a short path. We see the scattered blue light all around us. But at sunset, that path is so long that almost all of the blue light gets scattered away from our direct line of sight before it can even reach us. So what's left over? Exactly.
All that's left for us to see coming directly from the sun are the colors that don't scatter easily, those long wavelength reds, oranges, and yellows. And that is why we get those absolutely spectacular, fiery sunsets. It's the leftover light from a really, really long journey.
So, after a trip through light, air, and the physics of scattering, let's put all the pieces of this puzzle together and get to our final answer. First, let's just be crystal clear about what it's not. It has absolutely nothing to do with reflecting the blue color of the oceans. That's a super common myth. And it's not some kind of default background color for the universe. It's an active, dynamic process that's happening all the time.
So, it all comes down to these three ingredients. You need sunlight with its full rainbow of colors. You need an atmosphere that's jam-packed with tiny particles. And you need the physics of Rayleigh scattering to bounce that blue light in every possible direction. That combination, that is why our sky is blue.
And that's really the coolest part, isn't it? The color of the sky isn't just a static fact. It's a constant, beautiful physics demonstration that's happening on a planetary scale every single day. It's a reminder that sometimes the most common, everyday things we see are actually the result of the most incredible science. So the next time you look up, what else might you see a little differently?